you, Yin. Hi, everyone. I would like to talk about Lagrangian Coherent Track Initialization, LCTI. This is actually basically is a complementary function of KLPT, thanks to Yin that explained that the algorithm and what's the result of using KLPT. Well, I'm from INRAD actor group. I'm PhD student of this group, working with Dominic and Yin. Okay, well, I would like to start with basic questions. For the first question, what are the recent advances in volumetric PTV? I just list the previous talks for today. Well, we talked about check the box and so ensemble PTV, LAPI, KLPT, and also we do have some commercial, well, in addition to that, commercial studies packages like Lagrangian, TSI, and open sources studies like OpenPTV, OpenLPT, and so on. But what we are looking for in this presentation, we are looking to add physics-based information in our 4D PTV algorithm. So this is the question that we are looking for. And well, to address this question, we would like to add coherent information that we can get from local physics around each particle to improve our 4D PTV. To start, we start with track initialization. Well, let me explain a bit about what I'm going to present. First, 4D PTV principle, then what is track initialization, then what we mean by coherent track initialization, cluster of coherent particles, the idea of using LCS, Lagrangian Coherent Structures, and then some analysis in synthetic data for the cylinder wake flow. And well, I will talk about coherent lengths and time scales, and the experiment case, like what Yin presented, jet impingement case, and the LPT challenge, just one slide presentation. Well, for the PTV working flow, as Sean's presented very well, we have, first we start with IPR. We have some triangulation and shaking to get optimized position in the world space. And then we switch into track initialization, where we create tracks out of 4 to 5 time steps. Then we have tracklets with lengths of 4 to 5. Then we switch into optimization, which is we have prediction and optimization in this box to continue tracks. During this process, we always have some residual images, and we always have some new interior particles. These are things that I would like to mention. Well, during the 4D PTV algorithm, we faced some problems. For example, when you have a very low initialization numbers, at the end you won't get convergence, or when you cannot reconstruct new interior particles very well, at the end you will have problem, or you don't deal with lost particles, you don't have problems. So we do have three motivations to improve track initialization. That's why we used LCTI. In terms of track initialization, well, we have very basic technique, 4-frame technique, which is a 4-frame best estimate nearest neighbor. You try to look for possible tracks in 4-frame, which is, you can see possible tracks in 4-frame by nearest neighbor. Or, well, it works in low densities when you have very little intersection, but well, it doesn't work very well when you have complexities. Well, there's another technique, 4-frame best estimate enhanced track initialization. This one actually works on all the possibilities around your particle and tries to find unique solution for that. This one introduced in 2019, I guess. And this method works better than nearest neighbor, but still you have problems when you have complexities. What we say that we keep the same 4-frame technique, but we add coherency. We say, okay, particles are not alone in our domain, either in 2D or 3D. So they act coherent with their neighbors, not all the neighbors. Some neighbors are not coherent. So that's all the motivation that we want. We want to use this information that we have coherency in order to build unique coherent tracks. Well, if you look at here, I put some different time steps of particles in, well, let's say 2D homogeneous isotropic turbulence. You do have clusters of particle motions. Like here, you do have clusters of vortices which are very close to each other. You cannot say, okay, they are behaving 100% same as each other. But you have to distinguish between clusters of particles. That's basically what you see. For example, in cluster blue, you have particles rotating in different direction than particles in the red cluster. This is very simplified model of particle motions when you have complexities. So, well, just assume we have a target particle. This is the dark blue one. We would like to find the coherency between this particle and its neighbors. You can see the red particle is also neighbor with your particle, but you cannot say it is coherent. Well, there are some techniques that they are already working on it in some algorithms. For example, they say, okay, if standard deviations of velocity between your neighbors is lower than a specific value, okay, let's say this track is valid. Or if deviation of velocity between your neighbors changes, okay, this is valid. But I would like to mention that, okay, sometimes you have separations and it happens when you have complex motions. So you shouldn't take into account these particles. You should only work on particles that belong to each other. So here we use the idea of LCS, Lagrangian Coherent Structures. This LCS is developed in mathematical communities. They are working a lot on it, but we want to use the advantage of this technique in our PTV algorithm. We are working in Lagrangian frame, so we would like to use it. In order to get Lagrangian coherent structures, we need to, well, this is one way. You have a couple of different techniques. You need to identify parameters, scalar parameters called FTLE, Finite Time Lyapunov Exponent. Just assume you have flow map of your domain, 2D or 3D, and each trajectory is a part of your flow map. So you have phi in spatial temporal trajectory information that can be considered as your flow map. And you want to see what's happening between this trajectory and with its neighbors. So you define vector displacement between two neighbors. This vector displacement evolves during different time steps. So you have finite time, temporal information, and this is neighbor information. So you have spatial information. So you have vector displacement in spatial and temporal. If you just use the Taylor series and just take the first term of that series, you come up with a tensor. We call it deformation tensor. This tensor is very important because it has information of whether you have expansions, whether you have contractions, whether you have rotations. These are informations that you can get by this vector displacement. If you get the magnitude of this deformation gradients, you come up with Cauchy deformation tensor. This tensor, by identifying eigenvalue of this tensor, you can come up with solution to see the sign of separation between two particles. So you can, if you get the eigenvalue of these matrices, you will have information, you will have physics. Well, definition of FTLE is using maximum eigenvalue of the Cauchy green deformation tensor as a parameter to calculate scalar value of FTLE. At the end, I would like to say, if maximum eigenvalue, lambda max, becomes larger than 1, this is based on FTLE definitions and what we see in Lagrangian coherent structures. If it becomes larger than 1, then eigenvector corresponding to that eigenvalue shows the direction of separation. So this is really good news. You have information of your separation, you know the sign of separation is happening, and you know the direction of that. So this is information that we use to identify whether particles are coherent or not. Well, in order to see the difference between between LCTI and other four-frame based techniques, to see whether this idea is working or not, we analyze the three different techniques in synthetic data. Well, our domain of interest is, well, we have DNS results for 3900 in 10D 8 by 6D, but we only took 422 because the wake region, well, is one of the most complex regions that you might have in this kind of cylinder wake flows. And in order to create trajectories, we used fourth order Ronkuta. And for the spatial scheme, we use trilinear interpolations. But now the question is, how many particles should we use? This is something that I would like to also discuss about it. And what would be the time step? If you assume this one is energy spectrum of turbulence of our case, and well, we have integral length scale, Taylor length scale, and Kolmogorov length scales. If you define different number of particles, you will need to see what would be the relation between your particle concentration and your turbulence scales. I can understand in communities we talk about PPP, particle per pixel. It's mostly computer vision aspect. But when you talk about turbulence, you do need to come up with, especially in volumetric case, you do need to come up with two metrics, which we call it particle per cubic Kolmogorov scale and particle per cubic integral scale. So now I can see if I have 2000 particles, what resolution I can resolve. I can resolve, well, integral scale, but I'm very close to Taylor scales. If you add 20,000 particles, you can resolve Taylor scale, but you are away from Kolmogorov scale by 200,000 particles. This is for Reynolds 3900, specifically for my case, so it can change for different cases. So for 200,000 time steps, particles, you can get close to Kolmogorov scale, but you are still away from that to 10 power minus 3, so 0.002 particle per Kolmogorov scale. So these are two metrics that I defined, and we selected these three particle concentrations. And also about temporal resolution, well, we want to have more realistic synthetic data, so we should use experimental informations what they had, and compare it with Kolmogorov time scale and DNS time scale time step to see where we are. For example, I put some different studies in terms of the ratio of time step acquisition frame that they have over Kolmogorov time scale in different Reynolds number. You can see in low Reynolds numbers, well, you can resolve up to Kolmogorov time scales, you even lower, but by increasing Reynolds number, you get far. So the ratio between your time step that you have in real experiments, of course, it is limited by the facilities, over Kolmogorov time scale is goes higher. So this one means, for example, if you have every 100 DNS time steps, you can have a resolution of 4.6. Your time step is 4.6 times larger than Kolmogorov time scale. So we took these three actually for DT over DT DNS, but I will explain the first three. Well, in our case, because we did some experiments, we haven't published yet in this one and this one. for Reynolds 300 and Reynolds 3900. In our cases, is more likely to happen for like, we have another experiment actually more likely to happen for every 100. The comparison with other techniques, one comparison with enhanced track initialization and the classic 4-frame based estimate in three different noise ratios and 3 different DTDNS spaces, 10, 50, 100, and 3 different particle per Kolmogorov scale concentrations. So in these in these 3 plots, you can see by increasing concentration, you do not have any problem when you are at DT over DTDNS at 10. You do not have any problem. So it is not fair to compare, to say, okay, I did my analysis in synthetic and I used very few DTDNS time steps, because even nearest neighbor can work when you have very small displacement between two time steps. But by increasing DTDNS, DT over DTDNS, you will have huge drop, which is were more likely to happen in real experiments. And also you can see that by adding noise levels, you do have almost linear drop in all the 3 techniques, LCTI and ETI, and 4-frame best estimate. Here is the analysis. Now I would like to talk about coherent motions. Well, as Yin explained in Lapiv, we can be more interested. We should be it should be more interesting that if we look at the group of particle motions instead of just only single particle trajectory. This is the same 3900 case, and I applied LCS function for a couple of particles to see coherencies. Well, here you can see, around the cylinder in this region, around the cylinder, you have different coherent motions, and specifically you have very huge separation in terms of trajectory, very close to a stagnation point. So you do have 2 different coherent motions. So you should not consider both of these 2 when you are doing, I don't know, some kind of median filter, median test or something. Well, this one would cause you some error or loss in this region. So you have a group of particle motions, and their time and length scales are as large as your integral scales. So you have large scale coherent motions. This is really important, and this is really good news for LCTI and using LCS, because you know in this region you have high coherency and you can trust on it. But if you go in the wake region, in this region, well, you do have different scenario. Of course, in the shear, away from the shear, here, these 2 regions, you have again large motions, group of large coherent motions. But when you go inside the wake, like inside the wake region, you do have very small displacements and very small length scales. This is exactly more or less like what Sean's presented today, different time scales. So here you can see inside the wake region, your coherent motion is temporally and especially shorter than when you are away that. So this kind of information would this kind of pre-knowledge, actually, you know, you have small displacement here. This kind of pre-knowledge would lead you higher accuracy in using LCS, or even in using multi time step, multi delta T shake the box, the one that Sean presented today. Well, let's move into the experimental case. In the jet impingement case, we have a density of 0.03. And here you can see trajectories. And we just only used IPR to reconstruct positions. and we didn't continue shake the box or KLPT. We just tried to reconstruct based on LCTI. And well, it's really good to say that we could build almost 2,800 tracks out of 3 to 4,000. So this is over than 70% you could track out from your IPR. But this is not the idea that we are implementing LCTI. This is just for visualizations of how LCTI could work in experiment. And also I should mention we had like 3 domain decompositions, 3 subvolumes away from the jet and the inside the jet and this circulation regions. So the parameters would be changed because maximum displacement would change. In this region, you don't even need to apply LCTI because the displacement is very small, even very simple for frame can track, but in these regions you can't use it. Well, in the challenge case, first I would like to address this plot. This is the for density 0.12. By increasing number of initialized tracks, this is the convergence plot of the trajectory in different time steps. If you have like, let's say 15,000 tracks at the beginning, your convergence would lead you 50,000 tracks. But if you start with 60,000 initialized tracks, you can get convergence after, let's say, 10 time steps, and then you can get quite good amounts of trajectories. So this is the importance of number of initialization, that you can see you need to have good initialization. I know Shake the Box is quite robust, but you need to have good initialization in some complex motions to finally get convergence. And here just a visualization of the same density, just to show some coherent motions in the challenge case. In conclusion, I would like to say that again, LCTI is complementary function for 4D PTV techniques like kernelized LPT and Shake the Box. And well, we do have coherent lengths and time scales, which can change different based on your flow properties. And this is the important one. Particles are not alone in the flow field. They behave coherent with each other. So for example, here you have coherent motion, here you have coherent motion. And the other one, well, the LCTI or LCS by its nature is very expensive in 3D domains, but I would mention that this expensive computation is only for single core calculation. If you go for GPU-based algorithms, I'm quite sure the cost would drop dramatically. And also, it's important to know that it's possible to have some trajectories alone inside your domain, because your, as I said, your particle per Kolmogorov scale is not well, your spatial resolution is not well enough, so you miss some small scale coherencies. But well, as long as you have coherent motions, you can get you can use the advantage of that. Well, that's it. Thank you for your attention. If you have any questions, I would be happy.
Thank you very much, Ali.